Again, my name is Eric Harder. I'm with AWS Elemental, and today I'll be talking about live streaming UHD 4K stacks using distributed encoding. All right, so first question you may have is, why are we live streaming in UHD 4K? The easy answer is that the bar has been raised for quality. Any of the major live streaming events that you see, especially sporting events like Wimbledon, IPL, Super Bowl, are all streamed in 4K this year. So our customers are really asking for us to raise the bar on quality, and 4K is becoming the standard. 4K versus 1080p, and for me, what I see is 4 times the compute workload and 4 times the number of uncompressed packets. So it becomes really a compute challenge for us as we move to 4K, and it really is something that became a bottleneck for what we're trying to do here. We've been doing 1080p for years now with no problem, but now 4K is really pushing the boundaries. So this is an example of sort of a basic end-to-end live stream workflow. You have the signal coming from the live venue. The contribution signal goes straight to the encoder, which is going to encode in 4K or whatever full stack that we have. It's going to be packaged up and sent to the CDN for delivery so that it can be viewed by the clients. When customers are wanting us to process 4K, this is sort of their non-negotiables, their iron triangle, which is latency. They want it to be close to the live edge as possible. Quality, they don't want to, they're sending us a 4K signal. They don't want to compromise that. They want the end user to see this crystal clear 4K signal. And they want operational simplicity. They don't want this to be a huge burden to manage, especially what we're going to see in the next slide here is when they have a really giant full UHD stack. So this is an example of what we're getting from our customers is you got 2 redundant 4K inputs that we have to process. Those are going to be encoded, and then they have 14 different encodes that they want us to create and send in real time. So you'll see like there's a full, not only are they wanting an AVC stack and the HEVC stack, but they want the 2 4K encodes on top of that. Previously, you might see these stacks sort of in separate channels, but now basically they say we want 1 channel, we want the full stack, and we want it all just to work magically, and we want to be able to manage it in 1 channel, easy peasy. So that became quite a challenge. And this kind of leads me to the problem, and the problem really is that in order to meet this criteria and support the full stack, we had to come up with a solution that would get us past what our current limitations were. And the current limitations is that our compute nodes could do that full HD and SD stack, but as soon as you add 1 4K, we exceed the compute power and we can't encode in real time. And then you throw on another 4K to that stack and you really are in trouble. So our original solution was, okay, we can give you 3 different channels and we can synchronize them using input time codes. But then you have some redundancy. They have to send their input to 3 different channels. It's a huge burden to manage, and it just becomes a really complex system for the customer control. And you go back to that iron triangle, they want operational simplicity. And also with just the synchronization of the time codes, that's a little wonky. It doesn't always work out perfectly. So that also is a challenge as well. So we had to come up with something to fix this solution. Here's an overview of our video, or just kind of a generic video processing pipeline. You have your live inputs coming in. They're decoded to separate the audio and the video. You have the image processing, which is going to do some color correction. It's going to scale to all the different resolutions that are required. Then we're going to send it over to be encoded. So we saw there was 14 encodes in that example. This is where those 14 encodes are going to happen. After those are done, the audio and video are muxed back together and then sent over to packaging. And the time from the live input to the time we send to packaging is considered, that's where the latency comes in. And then again, what I alluded to earlier is the problem was in this encode stage is as soon as we add those 4K encodes, we can't fit them in this compute stage. We can try, but then eventually we run out of performance and we start to get out of real time, and then now we're jeopardizing latency, or we're jeopardizing quality, or we're just running out of compute and, and it won't actually do the job at all. So the problem is also that we're already hitting the largest compute nodes that we have access to. So we realized we can't do this. We can't do all this workload in one machine. So we're going to have to find a way to spread the load out. So we said, well, we should use multiple machines. So we were able to say, if we could take these encodes and then put some on one machine and some on the other machines, we can now distribute this, which sounds great, and it makes sense. You want to distribute in your load. But the problem with this is we're dealing with 4K frames, and we're dealing with a large amount of data that needs to be sent from our main node to these other nodes, and then it has to come back as well. And so not only do we have all these frames we have to process, we have to send, if there's 14 outputs, that's a lot of data that's going to be sent over the network. And again, we have latency that we're worried about. And so if it takes too much time to send all these packets over to other machines to encode them and then send them back, we're also, we're able to encode, but then now we're not doing it in real time. We're not going to be able to satisfy the latency requirements. What's nice is that there's a new technology called CDI. And CDI is actually an open source technology. You all have access to the CDI SDK. We originally were using CDI to deliver high quality, like 4K inputs as an input to our tool. And we realized, like, well, actually CDI has a 100 gigabit per second connection, and we could use it to send these uncompressed 4K packets around and back, and we're not going to really lose a lot of latency. It actually only adds about one frame of latency, which is completely acceptable, and we have enough buffered up that it won't even move the needle. So what we decided is, like, well, what we can do is we can leverage this. There's certain EC2 instances that have these elastic fabric adapters, and they're used for high compute or high performance computing. So what we can do is we can offload these encodes onto those machines. We can hook it up via CDI to our existing flow and send those uncompressed 4K frames and all the other frames over to the machines using CDI, where they can be encoded, and then we can send them back to our original machine, and all within real time, all within the amount of time we need to maintain that latency contract. The question is how do you divide the workload too? We have this really nice pipeline, that we don't want to mess with. Originally, we thought, well, we can just, we could really have 3 things in parallel. We can move our processing over there. We can mux it all on separate machines. But when you're trying to decide what to distribute, you have to weigh in the risk. You have to weigh in sort of what makes sense to distribute, so on and so forth. And we thought really the encode is the only thing that we needed to parallelize. So we cut the data plane right after the image processing and said we're only going to send those encodes. Originally, it was quite simple that we were just using these local FIFOs where we just take a packet, send it on a pipeline, it goes to our encoder, and then it gets encoded and comes back on another pipeline, gets sent straight to the muxer. So what we did is just kind of reroute like a train track and said, instead of sending it on this local pipeline, we're just going to use CDI. We're going to send it remotely to these remote machines. The encode happens there, it gets sent back on another pipeline, and all the other parts of our compute stages, like the processing and the muxer, they don't know any difference. They have no idea anything's happening remotely. And so by intelligently dividing your data plane at the right points, you can reduce your risk and just kind of sort of minimize the solution so that you're only doing what is necessary to distribute. So that's really mostly what I have here. The certain other things I want to say is, CDI and EC2 are something that you all have access to. If your flows is in the cloud and you're looking to move data around quickly and you need a lot of throughput and it needed to be reliable and secure, this is a great solution. There's a lot of different companies using CDI in different variety of use cases, and it worked really well for us, especially when we're dealing with 4K, because it's so much data to pass around. It's so much data to move that you need something that's reliable and big. And yeah, that's all I got. Any questions? All right. Yes.
Can you come
Turn
here,
the
please?
microphone, yeah,
Oh,
yeah.
This one is fixed.
Does that one work?
Just a second. Where is the second mic?
The portable mic. We're good. We're still under 15 minutes. We got time.
So you are responsible for
Yeah, thank you. So my question is, for the diagram you first introduced the CDI,
Yeah.
why don't you move the CDI before the decoder?
I mean, it's a good question. We decided that really, you mean like why not do it earlier on?
Yeah.
So-
So you do distributed decoding and video processing
Right.
such that the data you send through the CDI actually is much smaller.
Yeah, I think that part of it was risk. Part of it is complexity. There is try to think the easiest way to answer it, but a lot of it was risk. So we knew that we really just had to focus on the encodes, and we could be sending that 4K over to the nodes, but try to think that it's a longer answer than maybe I have up here for a few minutes, but I definitely after this we can talk about it.
Yeah.
But there's multiple areas that I could get into, but it's definitely a good question. It's something I'll say that kind of the what's next question is we might move some of the image processing, like move some of the color correction, some of the scalars into some of the remote compute nodes as well, because that might be a little more efficient. So kind of a one-to-many versus a one-to-one sort of situation here. But yeah, we can talk later. I can give you a better
sure.
answer.
Thank you.
Sorry.
No problem. Thank you.
Hi.
Hi there. My question is about a transport protocol that you're using between the image processing nodes through
Yeah,
CDI
yeah.
and then back to the Muxer.
So actually, what we're doing here is we're just kind of taking the 4K frames and just putting them into just sort of our own custom buffer and just sending the buffer over CDI, and then when we get to the other end, we just decode and convert it back into a picture frame. So you have sort of a generic buffer that you kind of do, by just bit conversion from the picture to the buffer back to the picture when you get, and that goes pretty quickly. It definitely is harder for the 4K than other frames, but you do lose a little bit of time. But yeah, I mean, CDI allows you to, it knows about audio and video, but then we use actually a raw data version where you're just sending buffers.
Just a quick follow-up. Is that a reliable channel? Or
Oh
is
yeah.
it- okay.
If we lose one frame, we're in trouble. And so that's sort of the contract with CDI, is that it's secure and reliable, and it will not drop any frames. And if we dropped frames, we wouldn't really know how to recover very cleanly. So yeah, we definitely had to have that happen. All right.
So thank you very much.
All right, thanks everybody.